Honors Chemistry. This is Lesson 18 Answers video, Part 4, and we should be able to wrap up the rest of the problems on this. So let's go ahead and get started. So an aqueous solution of hydrochloric acid contains 36% HCl by mass. So calculate the mole fraction and then calculate the molarity of it. All right. So what is mole fraction? Let's go ahead and write that down. It's moles. Okay, it's moles of solute over moles of solution. And there could be more than one solute, so you'd pick one, and down here would be everything else that's in that solution. But in this case, it's only hydrochloric acid and water. Okay, so how do we deal with this? We talked about how do you deal with a percent mass. And what you do is this. Okay, so you get to select the size of the sample. All it's telling you is that 36% by mass, by number of grams, of the solution has to be your solute. So you get to choose how big the sample size is. So what you're always going to do is you select the size of the sample, you choose 100 grams of solution. All right, so that means if we have 100 grams of solution, and let me write what that means. And if you find it helpful to do this, it takes a few more strokes of the pencil here. But to write, instead of solution, writing what it is. It's HCl plus H2O. That's what the solution is. And I'm doing it that way for a reason that I'll show you in a minute. So if you chose 100 grams, that means 36 of the grams have to be the solute, HCl. You could have picked any two numbers where this over this is going to be 36%. But let's pick the obvious one, 100, because it's an easy number to work with. That means the number of grams of your solute is always going to be the same number as that percent like that. So that's how you always deal with a mass percent when they give you a mass percent. You convert it into grams over grams, because that's what mass percent is. All right, so we know how many grams of HCl we have, but how many grams of water? Well, that's really simple. The grams of H2O equals the grams of the two of them put together. So that's why I wrote it. That's why I wrote it like this. The grams of. So if you take the grams of the solution, that should be an O there. If you take the grams of the solution and subtract the grams of the HCl, which you know is 36, and you know this is 100, so this is 100 grams. This is 36 grams. Then that's going to equal 64 grams of H2O. Okay. 64 grams. So now you know grams of everything, grams of HCl, grams of H2O, okay? All right, so we have to get from grams to moles to do mole fraction here. So that means we have to figure out, use the molar mass to figure out how many moles is 36 grams of HCl and how many moles is 64 grams of H2O. So let's start with HCl, so 36 grams times 1 mole over, grab your periodic table, it's going to be 1.01 for the hydrogen, and the chlorine is going to be 35.45. You add those together, you get 36.46 grams. Molar mass, molar mass, molar mass. Remember that term. Grams of HCl cancels, and you end up with 0.987 moles of hydrochloric acid. Okay, do the same thing now with the 64 grams of H2O that you calculated you have. And how did we get that? We assumed we're going to use 100 grams. We get to pick it. Mass percent, you get to pick how much you're going to use. You're going to use 100 grams of solution. That means that 36% of that, or 36 grams, is HCl. So the difference between those two numbers is 64. 64 is going to be the grams of water. and molar mass of water we've done a lot of times before. And grams H2O cancels there and there, and you end up with 3.55. Okay, so if we take this formula and let's go ahead and find some space, we'll do it right here. It's going to be the moles of HCl, that's this. I won't even write moles because everything's in moles, so they're all going to cancel out. You're going to end up with no dimensions there. Okay, and then it's the moles of these two added together. This plus this added together. That should be 8.7. And that is going to equal, when you add all that up, it's going to equal 0.217. That's the mole fraction. It's that big X. I think it's drawn like that. I think I got it right. I might have it backwards. Anyway, that's it. The mole fraction. It has no dimensions because it's moles over moles. They canceled out. Okay, so that's the mole fraction. It's expressed as a decimal, but it's called mole fraction. Okay, now the second thing it asks you, this was A. This whole thing was A. All the way down to here, okay? The second thing, B, is molarity. Okay? So what is molarity? It's small m, first of all, and it's moles of HCl over kilograms of H2O. Okay, so we got moles of HCl right there. We already know that. And kilograms, well, we figured out already that we have 64 grams of H2O. So it's that much for every 64 grams of H2O. Now you're going to convert from grams to kilograms. We need it to be in kilograms, so it's the standard conversion. There's 1,000 grams for every 1 kilogram. Get that out of the way there. So grams of H2O cancels. So it's 0.987 times 1,000 divided by 64. And that's going to give you 15.42. 0.4 if you're doing significant figures. The 64, maybe it's 2. We'll go with that. Molal, M-O-L-A-L, molal, small m. Okay, so that's your answer for that entire problem. Okay, so go ahead and once you've done it, even see if you can do it a second time. Okay, even a third time, whatever it takes to where you know it and can do it off the top of your head. That's when you're moving towards doing the problems. All right, so be sure you can do those. All right, I'm going to move on. Okay, we're on 7-2. So how many grams of NaOH are required to produce 0.5 liters of 3.2 molar aqueous solution? So again, you're given two numbers, and we've seen this before and earlier. So, well, first of all, what are we looking for? We're looking for grams of NaOH. So let's go ahead and put that over here. Now, we've been presented with this before where you have two numbers. Let's just set down a rule. It may not be a 100% rule, but it's probably pretty close to all the time. That when you have a volume like this, or maybe a mass, and then a molarity, which is what this is, the molarity is going to be the one you start with, not the volume. This is going to be a conversion somewhere in your problem. And you'll learn to just kind of develop that sense. But let's just say as a rule, you're always going to start with the molarity. Now, I'm sure there's going to be an exception to that sometime. But pretty much that's what you do. So you're going to come over here. And remember how you write it. You don't write it capital M. You write it in its constituent units of measure, the units of measure that make it up. So that's going to be moles. And we're dealing with NaOH of the solute, so it's NaOH. And that's going to be over liters of solution. And I like to write the 1 in front of liters. You don't have to, but I like to do that. And that's liters of solution. That's NaOH plus water together. Okay? So look at what we're trying to do. We're trying to get from moles of NaOH to grams of NaOH. So what's that called? You should literally say it out loud until you stick. Moles to grams or grams to moles is called molar mass. Okay, so let's write that down. We can go ahead and do that now. 1 mole of NaOH. And you just go to your periodic table and add up Na, which is 22.99, plus hydrogen, which is 1.01, plus oxygen, which is 16. And it's going to give you exactly 40. Okay. So our first conversion, we're going to deal with the top first, and then we'll deal with the bottom second. Okay, let's just talk about the bottom, though. You start with liters of solution, you end up with nothing in the denominator. So somehow that liters of solution has to disappear. And if you remember from our earlier problem, how did that happen? Well, you've got this other number right here. That's going to be a conversion, and notice it's the same units there, so they're going to cancel out. Okay, so you're learning to look ahead as to how this problem is going to form itself. Okay, so let's go ahead and put our molar mass in. We're dealing only with the top right now, and that's going to be this. So moles of NaOH and moles of NaOH. So now grams of NaOH is what you want in the final answer. Now we have liters here and nothing here, so that means we have to put this liter up on the top. And you got to be sure it is of solution. It could be liters of just the solute or the solvent. So it says to produce 0.5 liters of 3.2 molar aqueous solution. So this is the volume of the entire solution. So that does check out. Liters of solution, liters of solution. And now you have no units of measure on the bottom, which is what you needed. And so you crunch the numbers on that. It here is 64 grams of NaOH is what you would need to mix this. So what your teacher's telling you to do is make lemonade. You need to make a half a liter. You know how much a liter is. You buy liter bottles of drinks. You need a half a liter. You want it to be a certain concentration. You don't want the lemonade to be too sweet and thick or too watery. So this is the concentration. And this is the lemonade mix. So it's how much of this do you put in to make this much lemonade at this level of sweetness or of concentration. All right. And that's what this problem is saying in terms of our lemonade example. Okay, so there you go. And now we'll move on. Okay, let's go on 7-4. You have 750 milliliters of 1 molar HCl solution. You would like to dilute this to 0.6 molar. So it's going from 1 molar to 0.6 molar. How much water should you add? So you made some lemonade, you had some water, you put in a bunch of scoops of the lemonade powder, you drank it, it's too strong. So you want to put more water in so it won't be as strong. That's called dilution, okay? It's when you add water to a solution to make it weaker, make it not as strong. And as a very simple formula, we talked about this a few problems back. It's the molarity before you added the water times the volume before you added the water is going to equal the molarity after you added the water times the volume after you added the water. So if you add volume, that is you add water, you make the volume greater, the molarity is going to go down. It's going to be less concentrated. Your lemonade is not going to be as sweet. Okay, so all this is a plug in the numbers. It's pretty easy. So our initial, you could think of this as initial. That's beginning. If you're not familiar with initial, it means beginning. And final. This is at the end when you've added the water. All right, so do you have to convert to liters here? No, not really. You're going to get an answer in volume, in liters. It's a volume. So milliliters is fine. It'll work. Okay, so what you have is 1 molar HCl. So, and you want to get to 6 molar, so it's simply going to be 1 molar times the volume is 750 milliliters. If you want to convert it to liters, you can. But that's going to cancel out. Equals, this is the molarity after. And then what you're trying to find out is what's that volume going to be after. Okay? Now be careful, there's a little bit of trick at the end of this question. Okay? So 1 times 750 milliliters equals 0.6 times V2. So you're going to divide both sides by 0.6. And molar are going to cancel out. So all you have left is milliliters. These cancel, by the way, too. So your V2 is going to be measured in milliliters. That's what you want. Okay. So it's going to be 750 milliliters divided by 0.6. And that's going to give you the volume equals 1250. That's how much volume you're going to have at the end. Okay. And that's in milliliters. And it's fine to leave it in milliliters here. Okay. Because anything else, any other unit canceled out. Okay, so say, okay, good, I got my answer. V2 is 1250. That's not the answer. Be careful, you read the question carefully. How much water should be added to the solution? So your V2 was 1250. Your initial volume was 750. So the amount you added is the difference between those two. So you can write that as, and that would be 500 milliliters. That's your final answer. Okay. All right. So again, this was not a formula that you were given in the instruction video, but you did see an earlier problem, and it's a pretty easy formula. So now you know how to use it. It's called a dilution problem. So one of the things in chemistry you have to learn to do is recognize what kind of problem are you dealing with. In this case, it's a dilution problem. Okay. All right. Okay. Let's keep going. Okay. Let's go on to 7.5. You notice that some of these problems, the ones we've just done, are easier than the 1A and 2A that we did earlier. I said those are two of the hardest problems on the assignment, and they really are. These are a little bit easier. So what I wanted to do is work you through these tough problems, have you practice those, and then when you get to these should seem easier. They won't totally seem easy. You still have to get used to seeing these and knowing how to reason them through, but hopefully they seem a little easier. So here we're calculating molarity, and our substance is MgNO3 2. Okay, so it's going to be some amount of moles 2. Okay, MgNO3 2. We'll talk to you how to deal with that. Okay. All right, and it says calculate the molarity of 540 grams in 250 milliliters of solution. Okay. And I forgot to put that over here. It's in 1 liter of solution, the two of them mixed together. Okay, so let's come over here. So what we have is we start with grams, and you have that many grams in 250 milliliters. So you can go ahead and put that down here. And it's of solution. So I'm hoping that a lot of you can look at this now and see, okay, the top is grams to moles. We know how to do that. The bottom is simply milliliters of solution to liters of solution. So there's two conversions, and I hope that you know how to do that. First thing we have to do, though, to do the top, is calculate the molar mass of this. So let's go ahead and do that down here. Magnesium. There's 1 magnesium. Now watch out on this molar mass calculation. That might be the hardest part of this problem. There's 1 magnesium, and it's 24.31 from the periodic table. Okay, now be careful here. There's nitrogen, it's NO3 inside these parentheses, so this 2 distributes. So there's 2 nitrogens. And nitrogen is 14.01 from the periodic table. Now, and there's 3 oxygens, but again, this 2 distributes to that as well, so there's 6 oxygens. Be sure you understand that concept. And oxygen, each one is 16. Okay, so we do that, and we add all of that up. And what we get here is 24.31. When you add all that up, you get 148.31 for the molar mass, 0.33 grams for the molar mass of this, so we can write that out. Okay, there's the conversion. So we need to get from grams to moles. We need grams to cancel out, so hope you all know how to do this. Okay, grams of magnesium nitrate cancels there and there. You have moles on the top, that's what you want, so you're done with the top. I'm not drawing this very straight, am I? But we're doing the best I can. Okay, now it's simply milliliters of solution to liters of solution, so milliliters, 1,000 milliliters of anything equals 1 liter of anything, but we're interested in solutions. So let me try to get this lined up a little better here. So it's going to be 1,000 milliliters over 1 liter. Milliliter solution, so the only thing on bottom is liters. There it is. Okay, so now you do the math. 0.54 times 1 times 1,000 divided by 250 divided by 148.33, and what I get for that is 0.0. I can have 3 significant figures, it looks like here. So 0.0146. That's 3 significant figures. And it's moles per liter, it's molarity, so we could put a big M there. Okay. All right. Okay, so we're going to move down here to this one. It's got quite a few things it's asking here. Some basic information, and it's asking for several things. By the way, I'm going to scratch 7-7. There's a typo in it. Rather than correct it, I think you've done enough problems. We'll just skip it. So 7-7, skip it. It's the very last problem. Skip it. Besides, we can use the space maybe to do this.